those are all great answers. And so we have actually our next guest speaker who is actually doing research on composites. So we're very excited. And so I'm gonna kind of turn this over to, I'll comment the slide, but to Troy, who is a PhD student in aeronautics and aeronautics engineering at the University of Washington. So Troy, it's your show now.
Hello, I'm Troy Nakagawa, and I'm a PhD student at the University of Washington in the Aeronautics and Astronautics department. So yeah, and I'll just do an introduction on what composites are. So a composite material is a material made from two or more constituent materials with significantly different properties that when combined produce a material with characteristics different from the individual components. So it's basically just, you just combine one or two materials and they remain separate. So like unlike a metal alloy like brass or steel where the different elements like combine, these still remain separate materials. So like a biological example is wood. There's like cellulose fibers and lignin. Then another biological one is actually the bones in our body. There's like softer proteins and also like harder minerals that make up bones. So that's also considered a composite. Then another one that we can see like every day is concrete, which is made up of like cement, sand, gravel. And then most of them have some sort of steel rebar or like reinforcements. And then what I work with is carbon fiber reinforced plastics, which is probably what a lot of people think of when they think of composites. But then there's also other fibers you can use, like glass fiber is another common sort of fiber reinforced composite. Next. Yeah, and then here's just like a classification of composites. So you can have like particle reinforced, like what cement or concrete is, where they have like gravel and sand inside the cement. And then there's also like more advanced ones where they actually have like carbon particles in it or like metal particles inside plastics, which is good for some manufacturing and like injection molding while bringing up some mechanical properties. There's like fiber reinforced, which is what I work with carbon fiber, where you can have long strands of carbon fiber, which is like a continuous fiber composite. And then there's discontinuous fiber, which is what I specifically work with. And that can be separated into aligned and randomly oriented. And I work with the randomly oriented discontinuous fiber composites. Then there's a structural one, which I think like the one most used is sandwich composites in planes. And also laminates are kind of a mix between, because we also call like continuous fiber, like the plates we get from them, we call them laminates as well. But yeah, sandwich composites are typically, you use them because most of the stresses will be on the outside of your part. So like you don't really need to make a laminate that's like 10 inches thick. You can maybe just have like 1 inch on the top and bottom made out of the carbon fiber, which is stronger. And then you can do like this where there's a honeycomb structure in the middle. So that way you save weight and it still keeps like a lot of the, I guess, mechanical properties needed for the application. Next. So then why do we use composites? A lot of times the individual components aren't really great for the job. Like for carbon fiber, you can't really just have loose fibers, even though they're really strong. If you just had a bunch of loose fibers, it would kind of be like trying to build something out of your hair. So you need something to put it in. And then plastics, they're typically really ductile, but they're easy to make. So it's like really great to combine the two. And then you can see this chart is actually a chart of a bunch of different materials, with the y-axis is the strength of the material, and then the x is the density. So you can see like carbon fiber, which is this, what does that be, like a brownish color, is, it is stronger than a lot of metals, but still like a lot less dense. So I think the strength of carbon fiber is about the same strength as a lot of aluminum alloys, but they're a lot lighter. I think aluminum is around 2.7 grams per centimeter cube, while carbon fiber is around 1.6. So this is especially great for, aerospace applications or like cars, where the more weight, the more fuel you need. So yeah. Next. Yeah. So here's some applications. So there's a Boeing 787, which is 50% composites by weight. And there's other planes made up of a lot of composites. Like I think Airbus has one, and like a lot of jets are made of composites now. And then another one would be like plywood, which is wood, which is a biological composite. Then as well as there's composite countertops now, which are normally made from like a recycled like wood chips. And then they typically are in some sort of like resin. Then you also have like a lot of carbon fiber in cars. Like this is a Porsche, but there's also like Lamborghini uses composites, and McLaren and a lot of F1 cars for its lightweight and also for strength. And then you have a lot of sports. I think a teacher mentioned like lacrosse and hockey, but tennis, they have baseball bats made out of composites now. A lot of bikes are being made out of composites. So there's like a lot of applications. Yeah. And then here's some like more recent research that's going on with composites. So one that at our university, we have a lab that's actually working on composite origami. And specifically, they're working on a lot with the to soften impacts of like, so they imagine maybe something like how SpaceX are trying to make reusable rockets. So like with composite origamis, because it's not completely made out of like a one material, and it kind of, the joints have kind of a flex to them, they can be a lot more like a spring sort of material where it can dissipate a lot more energy when it's landing. And then also another thing for origami composites is for deployable structures. So for aerospace applications would be like you can send up something lightweight, like carbon fiber, fold it out, so it saves a ton of volume where they can fill it in with other stuff. And then once it's in space, it can unfold to the shape they want. And then in space, now they're developing UV cured resins. So it'll just cure on its own from the sun. And then there's automated fiber placement, because now a lot of structures are being made like really large, like planes. And this is a fuel tank that NASA made. So you can't really lay up all the plies by hand. So there's a lot of research being done on the automated fiber placement and optimizing the path that it takes to take the shortest amount of time. And then what I'm working on is this discontinuous fiber composite, which is has a lot of advantages over continuous fiber because of its manufacturability. With continuous fiber, because it's all one long strand, a lot of times it's hard to make complicated geometries. So like, since this is all like separate platelets, it's a lot more bendable and flexible to do these complicated geometries. And then another aspect that we're researching now is with recycling, because with all these demands for carbon fiber, there's going to be a lot more waste. So you'll have these sheets of carbon fiber with just like a hole cut out in it. So all the scrap waste on the sides can just be cut up into these platelets and be made into whatever, rather than now they typically get rid of the resin on the fibers by like burning it or putting it into some sort of acid like sulfuric acid, which could be pretty dangerous. So yeah.
Oh. Wow, thank you, Troy. That's pretty cool. Didn't know like composites could be like so cool. But that's pretty neat. Wow, I didn't know about the origami type. Yeah. Anybody have any questions for Troy? Yeah, it's a pretty cool research that you and you're doing at your university. Yeah, no one has questions. But you can always put it in the chat, and Troy can kind of get back to you if you have some questions on composites in general. Okay, all right. Well, thank you, Troy, for sharing. We will get back to Troy at the end. He'll tell us more about his journey and his story. But thank you, Troy.